Why are transfer functions crucial in system dynamics? Imagine trying to understand how a car's engine responds to different speeds without any clear measurements. It would be quite challenging, right? This is where transfer functions come into play in system dynamics. They are essential for understanding the relationship between inputs and outputs in mechanical systems. At their core, transfer functions provide a mathematical way to representing how a system behaves. They specifically apply to linear time-invariant systems, which are common in mechanical engineering. By using transfer functions, engineers can analyze and predict how systems will react under various conditions. A transfer function is essentially the ratio of the Laplace transform of the output to the Laplace transform of the input. This approach simplifies complex differential equations into easier algebraic forms. This transformation is a game changer for engineers, allowing them to focus on design and analysis without getting bogged down in complicated calculations. One of the key uses of transfer functions is in system stability analysis. By looking at the poles of the transfer function, engineers can determine if a system is stable, unstable, or marginally stable. Stability is vital in mechanical systems to ensure they operate safely and predictably. Poles with negative real parts indicate stability, while those with positive real parts suggest instability. Transfer functions also help evaluate system responses. Engineers can study how a system reacts over time or frequency to different inputs. This includes analyzing time domain responses, like step or impulse responses, and frequency domain responses, such as resonance and bandwidth. This information is crucial for understanding how mechanical systems respond to forces or control inputs. In control system design, transfer functions are foundational. They allow engineers to model the dynamics of a process and design feedback controllers that meet performance goals. For example, in robotic arms or vehicle suspensions, transfer functions help maintain desired positions or speeds despite external disturbances. Mechanical systems often consist of multiple components that interact dynamically. Transfer functions simplify these interactions into manageable models. This allows engineers to predict how a system will behave under various operating conditions. Another benefit of transfer functions is their compatibility with graphical representations. Engineers can use block diagrams to visualize complex systems, where each block represents a component with its own transfer function. This modular approach makes it easier to analyze and understand the overall system. In practical applications, transfer functions assist engineers in predicting vibrations in structures, designing effective suspension systems, and developing precise temperature control systems. They also help analyze the dynamic behavior of various mechanical components. Overall, transfer functions translate physical behaviors into mathematical models that engineers can manipulate and control. This capability is why they are so important in system dynamics and control engineering within mechanical engineering.